Hello and Assalamualaikum. My name is Danish Bezukifli. Along with my teammates Trish, Danish Haikal and Tivesh, we will be presenting our neural network group project, which is early detection of diabetes risk. So to start it off, diabetes mellitus is a chronic disease that occurs when the body is unable to produce sufficient insulin or use it effectively, which causes high blood glucose levels. Early detection of diabetes is important because delayed diagnosis can lead to serious health complications such as heart disease, kidney failure, blindness, and nerve damage. With the advancement of AI, machine learning techniques can assist healthcare professionals in identifying individuals at risk of developing diabetes more efficiently. In this project, we uses the PIMA Indians diabetes dataset to develop a feed-forward neural network trained using the backpropagation algorithm. The model analyzes patient health data and predicts whether a person is at risk of diabetes. The main objective of this project is to develop an accurate prediction system that can support early diagnosis and improve diabetes management.
Now we're going to be entering into the raw data description. So our dataset was actually taken from the Pima Indians diabetes dataset, which was found in Kaggle. So the total records for this entire dataset is around 768 patient records, and there are a total of 9 columns of attributes. So there are a few input attributes that we put into this project, which is pregnancy, glucose, blood pressure, skin thickness, insulin, BMI, diabetes, pedigree function, and as well as the age. So there are a few target attributes that we put, which is 0 for non-diabetic and 1 for diabetic. So what is the purpose of the dataset? So the purpose of the dataset is used to train and test the feed-forward neural network system. So this enables the prediction of whether a patient is at risk of diabetes based on medical measurements. And we have a few Python library used. We use two in this system or in this project, which is the Panda libraries and the NumPy. So the Pandas libraries, we use the pdread CSV to read the CSV file. We use dfhead to display first few records, dfinfo to view the structure of the dataset. So we know what is inside of this, especially for everything details such as the structure, the data types, the non-null values, because there is a lot within a raw dataset. And we also show df is null sum, so to identify missing values from any column within the raw dataset. And then to drop duplicates, which is to remove and to duplicate records. To remove duplicate records within the dataset. And then we have df final to replace missing values, and as well as dtdf.tocsv, which is to clean the new dataset into a new CSV file. And we also use the NumPy, which is the np.nan, to represent missing or invalid values during the pre-processing stage. So in this system, we are using two deep learning techniques, which is the feed forward and as well as the back propagation. So the feed forward here is actually a supervised neural network where data flows from input layer through hidden layers into the output layer. So it's usually used to classify the patients, whether they are diabetic or non-diabetic, which is the ones and the zeros, based on the health attributes within the CSV file. Backpropagation, on the other hand, is to train the algorithm to minimize prediction error. So it will update the weight by propagating errors through what we call through backward propagation through the network. It also helps to improve the model accuracy during the learning process. So when we use backpropagation and feedforward propagation, it helps to bring the system together by both supervised and also having the system learn on its own.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Danish Haikal bin Muhammad Sufyan, and now I will explain the training phase of our early detection of diabetes risk system. So, the training process begins by loading the diabetes dataset, which contains patient health information such as glucose level, BMI, blood pressure, age, insulin level, and other relevant attributes. Next, the data undergoes pre-processing to handle missing values, remove inconsistencies, and normalize the data. These steps ensures that all input features are in a suitable format for the neural network. After pre-processing, the neural network is initialized with random weights and bias. During the feed-forward process, the input data is passed through the network from the input layer to the hidden layer and finally to the output layer to generate a prediction. The predicted output is then compared with the actual target value to calculate the error. The backpropagation algorithm uses this error to adjust the weights and biases in the network. The objective is to minimize the error and improve prediction accuracy. This process is repeated for all training samples in one epoch. Multiple epochs are performed until the error reaches an acceptable level or the maximum number of epochs is reached. At the end of the training phase, the network has learned the patterns within the diabetes dataset and produced a trained model that can be used for prediction. After the training phase is completed, the system enters the prediction phase. In this phase, a new patient's health information is entered into the system. The input data includes the same features used during training, such as glucose level, BMI, blood pressure, and age. The new data first undergoes the same pre-processing steps to ensure consistency with the training data. The processed data is then passed into the trained neural network. Unlike the training phase, no weight updates occur during prediction. The network simply uses the knowledge it has learned to generate an output. Based on the output value, the system determines the patient's diabetes risk level. The result can be classified as low risk, moderate risk, or high risk depending on the prediction score. Finally, the risk assessment is displayed to the user, allowing for early awareness and encouraging further medical consultation if necessary. That's all from me. Thank you.
This is our model's results. It has an accuracy of 77%, so it could accurately predict around 77 of 100 patients, and it also has a precision of 63%, so it can accurately predict patient that had diabetes for around 64% of the time. Uh, it also will have very good recall value. It can it can identify actually diabetic patient around 81% of the time. It is a good thing in a medical setting, and it has a decent score of 71% F1 score, so it does show it has a good balance between our prediction and recall. And our AUC score is around 83%, so it tells that our model can differentiate between a diabetic and a non-diabetic patients. And as you can see, the confidence metric, it has very less true false negative group, which is a good thing in medical setting, and and it can also detect around false true positive around like 41 people, which is also a good thing. It's fine if the model have a lot of false positive in a medical setting, but it might be a bad thing if it's a lot of false negative. As you can see from our classification result, our model performed well on identifying diabetic patient. It has a it is capable of differentiating two different classes, as you can see from the AUC value. Uh, However, a patient for diabetic patient is low, meaning um, non-diabetic patients will be incorrectly classified as diabetic patients. Um, Overall, this feed-forward neural network should able to help professionals to screen patients and can be used as a reasonable tool for early diabetes detection. In conclusion, our model has reached around 73% prediction accuracy, and our model has been capable of proving its effectiveness of the backpropagation neural network for database classification. If we talk about the future improvement we can make, that will be using a larger data set, we're doing some feature engineering and also some hyperparameter tuning. Thank you.